Greetings. Welcome to SAMPI's Technical Committee webinar. Greetings. My name is Raj Manchanda. I'm the Chief Technology Officer. I'm going to introduce our moderator in 1 second, but before I do so, I wanted to welcome you to the SAMPI Technical Committee webinar on sustainable manufacturing at Oak Ridge National Laboratory, ORNL, and IACMI, the Composites Institute. For those of you joining, please go ahead and in the chat, enter in your name, your title, your company name, and your geographic location. So once again, in the chat, please enter in your name, your title, your company name, and your geographic location in the chat. Professor Zhe Huang is the moderator for today's webinar. Zhe is assistant professor at the University of Southern Mississippi. Thank you, Zhe. Please.
Thank you. All right. Should we wait for another minute or we can just start?
You can, I think you can start the introductions.
All right, no problem. So again, welcome everyone. And today it's a great pleasure to have this webinar, Sustainable Manufacturing at Oak Ridge National Lab and the Composite Institute, Circular Economy here. And then first of all, my name is Zhe Qiang. I'm a faculty member at the University of Mississippi, like Raj said. And I'm very glad to serve as a moderator for today's webinar. A couple of notes before I start this webinar introducing our speakers. This webinar will be recorded and the link to the webinar will be shared and the slide deck will be available as well. So for those of you interested, we will follow up with an email about the link and other informations. The second is that during the talk, if you have any questions, please type your question in the Q&A box and I will read off after the webinar is finished and we will have a Q&A session for all the fellows here to answer and discuss the questions here. All right.
So I was going to say, I forgot to mention, you are chair of the SAMPI Sustainability Technical Committee. So if you have any few comments about that, that would be fine.
Yes, thanks for the reminder. And also I'm serving as the chair of the Sustainability Tech Committee under the SAMPI here. We are a tech committee that meets monthly to discuss the progress in sustainability in the broad definition of the advanced materials. So we talk a lot about recycling, upcycling, as well as develop new sustainable materials, including using bio-derived source and renewable energy here. So we have a group of over 100 people in our committee here. And like I said, we meet monthly and typically we have a monthly webinar seminar as well. So if you're interested in joining our tech committee, you're more than welcome to reach out to me, Raj, any people, and we will put you on a calendar and schedule here. So, all right, with that, I'm very excited today to introduce a group of very accomplished scientists here as our webinar speakers. And first of all, Dr. Soyundan Ozan is a distinguished scientist and the group leader for the Sustainable Manufacturing Technologies Group at Oak Ridge National Lab. He also holds a position of a professorship in the Department of Mechanical, Aerospace, and Biomedical Engineering at the University of Tennessee, Knoxville, and served as the lead for the ACMI Circular Economy Pillar. The second speaker is Uday Vaidya, serves as the Chief Technology Officer of ACMI, the Composite Institute. He holds the Governor's Chair in Advanced Composites Manufacturing, a joint position at the University of Tennessee, Knoxville, and Oak Ridge National Lab. Additionally, he is the Editor-in-Chief for Composite Part B Engineering and was named a SAMPI and SPE Fellow. Dr. Kate Clarkson is an Associate R&D Staff Member at Oak Ridge National Lab in the Sustainable Manufacturing Technologies Group. She is also the co-chair of the Sustainable Materials and Manufacturing Analysis for Renewable Renewable Technologies Research Experience for undergrads. Dr. Hillel Tekinep is a senior R&D scientist at Oak Ridge National Lab in the Sustainable Manufacturing Technology Group. He's the co-principal investigator for the Sustainable Materials and Manufacturing Alliance for Renewable Technologies research program with the University of Maine. Dr. Matthew Corey is an associate R&D staff member at the Oak Ridge National Lab in the Sustainable Manufacturing Technologies Group. He is also an assistant professor in the Department of Mechanical, Aerospace, and Biomedical Engineering at the University of Tennessee, Knoxville, and served as co-chair of the ACMI Circular Economy Working Group at ACMI. Sona Elias leads and manages industrial collaborations for the Sustainable Manufacturing Technologies and Composite Innovation Groups at Oak Ridge National Lab. She currently serves as the Vice President in the SAMPI North American Executive Cabinet and as STEM Advisor for the Society of Warm Engineers Smoky Mountain Section. Again, it's my great honor to have all these speakers here today, and then please start.
Thank you very much, Professor Kwang, for this great introduction. And good morning, good afternoon, everyone. And thank you to everyone who made time to join us today. And I would like to extend my thanks to SAMPI, who made this opportunity possible for all of us, and also for their indispensable service to this community. As you all know, we will have a discussion around the sustainability. So I would like to start the definition of sustainability. In here, sustainability is fulfilling the needs of current generations without compromising the needs of future generations, while ensuring a balance between economic growth, environmental care, and social well-being. So it's an umbrella term that includes many factors to be counted, such as decarbonization, climate change mitigation, circular economy, resource management, and social equity. So in this content, my colleagues and I will summarize today our previous and current activities within our group in Oak Ridge National Laboratory, as well as within the Composite Institute, IACMI. And also we include some activities about the SMART program with University of Maine. I hope this will set the stage for questions and discussions at the end of the presentation. Within IACMI, our focus has been composite materials, particularly being in wind energy, automotive, and aerospace. We have put together over the time 2 roadmaps. One of them is 2016, another one 2017, with a wide participation of the industry. I would suggest you to check this document. These roadmaps are available. And since 2015, next slide, please. And our focus has been on building sustainability consortia within the country, within the US, to work with an industry, to work with university, and to work with the nonprofit organizations. As in this example, the first one we chartered in 2016 with the Composite Recycling Technology Center in Port Angeles. And we built many of those relationships with our industry partners. And in this perspective, we facilitated and mentored many students. We have taken steps to initiate the movement in this direction. Examples are, provided in this slide. We educate and train future leaders in this area by investing in workforce and programs. During that time, we have done workshops, panels at CAMEX, SAMPI, and also support the formation of the Sustainability Coalition within the ACMA. And we started 8 projects on recycling and reuse. As you see in this example, more than 30 different organizations involved in our program. And to go through our example projects and activities, I'm going to hand over to Professor Vaidya to continue on our presentation.
Thank you, Sardan, for that wonderful introduction. Good afternoon, everyone. Thanks for joining us. We really appreciate it. So like Sardan said, there's been a lot of activity across these 2015 onwards in composite recycling in the US, and large part goes to Sardan and his group for initiating and enabling this. So I would like to mention that the recycling portfolio for IACMI is fairly broad. We're looking at solutions for wind blade recycling, for example, a lot of landfill, end-of-life blades, automotive parts, end-of-life automotive parts, and manufacturing waste, agricultural equipment, and agricultural waste, as well as construction vehicle parts. And as you know, the sources for these come from a range of materials, whether it's glass fiber, carbon fiber, mixed reinforcements, a range of polymers, thermoset, thermoplastic. So the comprehensive strategy for recycling has not been really available. And through many of the efforts from these groups that you're hearing today, this has now become a possibility, whether it's pyrolysis, solvolysis, thermolysis, cement kiln, or shredding. Any of those become very viable in terms of defining the lower upper bound for designers to use in their applications. Next slide, please. So one such example that has gone from concept to commercialization is the work IACMI has done with the Composite Application Group in Knoxville, Oak Ridge National Lab, University of Tennessee, and a host of industry partners is with this company called GreenTex in South Carolina, which basically had a concept of using manufacturing residue all the way from as like end of life parts, as well as manufacturing waste like shredded fibers and offcuts and things of that nature. So the Jay Holmes, who is the CEO for GreenTex, had a concept of a simple shredding and coming up with blended resins to produce panelized constructions 5 feet by 12 feet or something that's representative. It started off as a concept for marine shipping containers, and then eventually now it has taken on in areas of trailer tractor decking and other walls and applications that normally were not initially conceived of, but now have become available because of all the groundwork done from the understanding the material constituents, their mixes, proportionality, property bounds, and how do you actually process with them to a stream that now becomes very tangible product. So this has been a good example for IACMI. Next one, please. And in another project, basically the entire closing the automotive loop has been demonstrated all the way from starting material. Vertega, which is the company on the bottom left, was essentially a startup in Colorado, and now they have really expanded in a major way in carbon fiber recycling using solvolysis. So the waste coming off from that in terms of hairy tangled mass, for example, of carbon fiber, processing that into intermediates that are actually processable for compounding and blending and other forms, mats and other usable intermediates, going into processes like compression molding, injection molding. This is the scale-up facility in Michigan of IACMI in the middle there. And then these full-scale parts using automotive relevant tooling has been gone into demonstrating things like the quarter fender on the right-hand side bottom there, as well as tailgate panels. So going from essentially all the way from waste to product has been demonstrated through multiple partnerships. So that's been very valuable. And I'd like to now hand this to Kate for going into more details.
Right. Thanks for that great example, Dr. Vadia. So between ORNL and IACMI, we've developed large-scale capability to process composites back into intermediate feedstocks and eventually back into parts as well. So over here on the left side of the screen, you'll see an overview of our approach to creating a circular economy for composite materials. So we basically take or customize an adaptable approach depending on the material that we want to recover. But most of the time, regardless of whether it's a thermoset or a thermoplastic composite, we have a desizing step that can break the material down into more manageable pieces, and then a separation of material streams. So for instance, removing metal contaminants or sorting material streams if there's more than one in the waste stream. After that, the approach is focused on what we want to recover. So for instance, developing a recovery pathway for fiber reinforcement, which we just saw an example of. We'll see another example at the end from a different colleague. But then after we've recovered the material that we want, whether that's the thermoplastic composite feedstock itself or a fiber that we've recovered from something like a thermoset composite, we can process those materials back into intermediate feedstocks as well. So over here in the bottom left, we have a couple of different research spaces in our portfolio, and I'll give you a few snippets from active research areas that we have going on. So for instance, our next generation materials development, we are developing inherently more recyclable resins, so Vitromer type of materials. We also work a lot with commercial companies that have already created those types of resins to create parts and demonstrate the utility of them in different application spaces. Another big one for us is a design for sustainability. So how can we change product designs to make them easier to recycle at the end of life or reuse composites into new applications? So for instance, I have a colleague that does a lot of work basically repurposing end-of-life wind blades back into commercial products. And then, of course, all of our research is coupled with this real-time life cycle and techno-economic analysis that we can do in-house to help validate the environmental claims that we are learning about in our research. So for our next slide, we have built up equipment capability and knowledge in this area. So here's an example of some of our equipment capability for recovering different material streams. So from the equipment here, you can imagine being a company, we can help you figure out an approach that makes sense for your materials. All of this is fully integrated with sensor technology that can be used to develop life cycle assessment and techno-economic analysis models that ultimately validate your approach. So for instance, we're really taking whatever the problem is for the company and connecting them with equipment capabilities and process know-how to further the reuse of their materials, whether that's into their own stream, into their own products, or tying into somebody else's. So with that, I'm going to go ahead and pass this on to my colleague, Dr. Halil Teknalp, who's going to provide you some more examples of our research in this space.
Thank you, Kate. So I would like to talk about one of the specific projects, including this area in collaboration with University of Maine and Unistress. So this is a technical collaboration project between under the SMART program that we have with University of Maine and with an industrial partner. So in this project, we are looking into recycling of precast concrete formworks. So the precast concrete formworks are used to produce specific shape concrete parts, which is mostly utilized in the building and construction industry. And usually they're traditionally made using wooden panels. Although they look very simple, actually during the production, these wooden panels, the production is actually very labor intensive and tedious process. And usually after 4 or 5 pours, the formwork is actually start to deform, and it needs to be either repaired or remade. So this is very labor intensive process. So additive manufacturing was a great example to use in this application. And in one of our projects, earlier project with Case Construction, the Domino Sugar building in Brooklyn, New York, actually utilized these formworks, and then it was very successful. However, at the end of the life, what you're going to do with this formworks? You don't want to landfill them. So in this project, we are investigating recycling of these materials and then reuse them to similar application to see how the material properties are changing. And for this project, we were utilizing 2 different material feedstock. One is carbon fiber ABS, which is a petroleum-based system, and the other one is fully bio-based wood fiber PLA system. So in this project, we are printing these molds. We pour parts out of them, and then we clean them, and then using the capabilities you saw in the previous slides, that we're actually shredding and granulating them and then repelletizing them into uniform pellets, and we print them again. And we are repeating this cycle 5 times. And we are already in the 4th cycle. It's been working fine, and then we have no problem. And then we're investigating all the changes. And even in some cases, we see some interesting results that the materials preserving their properties really well, and we are able to actually produce concrete pours using the same material again and again and again. And this is showing how impactful recycling can be on this kind of materials. And with that, I'm going to pass the mic to my colleague, Dr. Matt Corey.
Dr. Teknalp. So I just wanted to highlight 2 more examples for everybody in the call. Oftentimes what will happen is, companies will approach us and they will say, hey, you're a national lab. We have a new material or a new part that we're putting out there made of a new material, and we don't know what to do with it at end of life. And so one of the big roles that our team will play is to help demonstrate that end of life and pull in the right supply chain partners that can process that end of life material. A good example of this is this collaborative technical collaboration we had with AirTech, who has a big 3D printing industry that's making large format additive manufactured parts. This project here, they were interested in making a new mold for the front splitter on a car that raced at Pikes Peak last year. They made the mold for the car just before this one in the last race, and they knew that they could do the design better. And so they asked if it'd be possible to take last year's mold and recycle it into this year's mold. The reason for that is because this material, it's thermoplastic, but it's actually quite expensive. And so this was tens of thousands of dollars for this one mold. And so Airtech really wanted to demonstrate the utility of this molding technology, but in order to do so, they needed to do it at a significant cost reduction. And so our team came in, we ended up demonstrating the mechanical recycling viability of this particular material. It worked extremely well. And we learned a lot from this project. Most importantly, that we saw a more than 90% reduction in the greenhouse gas emissions that were calculated from our LCA work, as well as a significant more than 95% reduction in the cost of the material. The reason for that is because the virgin mold uses carbon fiber filled polycarbonate. And when we're able to recycle it, we don't have to produce the carbon fiber anymore. And so you can basically do that at a significant cost and environmental impact reduction. And so it worked extremely well. And the car, they used this mold to make the new front splitter. They raced it and they set a new class record last year. And so this was one example of a project that worked really well and demonstrated the kind of end of life for these materials. Another good example is this project with Carbon Rivers, who's a thermal recycler for composite systems. So they have a process through which they generate a chopped glass fiber from end-of-life wind turbine blades and other glass fiber composites. And what their product is chopped, it's fluffy, it's a glass fiber. It's really challenging to recompound that back into plastic. And so they worked with us to develop the process on our equipment. We took the material in, we shredded it, we gave it to them. They took it and then they made it into the glass fiber using their thermal recycling process. And then they gave that fiber back to us and we recompounded it back into polypropylene in various loading levels. And then they used that with our help to make a bunch of different parts, which we then characterized, and then they were able to take that information to a bunch of different downstream partners. And so this was extremely interesting collaboration. And thanks to Carbon Rivers' efforts here, they were actually able to get their product into a commercial product, which is this Green Llama spray bottle cap on the top right. So you can actually go to Whole Foods and buy this product right now. This is manufactured by, it is material, 20% of the loading in that is glass fiber from wind turbine blades, end of life, and that is recycled in the U.S. in Knoxville, Tennessee, by this company, Carbon Rivers. And we work really closely with recyclers like this at the end of life, who they need help getting enough volume to do a demonstration of their technology and to help close the loop. And so, so with that in mind, this is kind of our bread and butter. If you have a material or you're looking at a new material, we can do this at a bunch of different scales, all the way from the benchtop scale, where we can take mechanical sample coupons from you and recycle them and help you understand what the recycled material will perform. We can do real-time LCA and TEA as well. So that's kind of the spiel I wanted to share with everybody today. And with that, I will pass it off to Sarah Elias, our head of industrial collaborations for the OMDF.
Thank you, and thank you to the panelists. Just want to go back in, share my screen. Good afternoon, and thank you everyone for joining in. You got a little bit of a spiel of, who we are and what we do, the kind of materials we touch, the kind of equipments we play with, and also some of our projects. So looking at, increasing the life or using it in as a secondary feedstock, many different ways of recycling, redesigning, and repurposing. How can we take that and learn from it? And also, why do we need to come together to do this? As a manufacturing demonstration facility, we are a user facility, and we want to make sure that we are enabling the workforce and also the industry to be ready for advanced technology, so they are able to stay ahead of the game. They are also able to provide newer solutions, which would be the need of tomorrow. How do you make that happen? There are different mechanisms. There are a few listed out here. Happy to take questions and address them. Tech collabs is something that we look at more often. So the collaborative research and development agreements and the user agreements, it can span anyway from about 6 months. It could go up to 24 months. There are more details to it. We'll be happy to talk to talk to it later on and take questions. Let's look at some numbers, right? So why do you want to do this? Let's say there's a new technology that's come up on a bench scale, and it seems like there's some feasibility. And it could be at a small business, it could be at an OEM, it could be even at a startup, but taking it from that bench scale up all the way to a place where, as Dr. Vaidya showed in one of his slides, you're looking at very high volume manufacturing. Now, the technology readiness level may not exist when the initial idea was developed. And that's where we come into play, whether it is through IACMI mechanisms or through Oak Ridge National Labs Manufacturing Demonstration Facility, Tech Labs. We are playing in the technology readiness level of 3 to 7. We're trying to bridge the gap. Also address the value of death for the startups, and see if there's any way with our knowledge and expertise and understanding, we de-risk those technologies. We give access to more than 100 advanced manufacturing systems and the researchers that we have on site here. If you look at on the bottom, there's a good spread in, we're not working in silo, we're not working with one company. Some of those examples that we walked through in the earlier slides, you were able to see that it's many different companies coming together. And we are trying to make sure that this work and our future work is helping the supply chain. And we are collaborating with everyone from a material supplier to an OEM to a tier company. So when the technology matures and it can be scaled up, there is no barrier for it left out. So we have a really good mechanism that we put forth here, and we look forward to growing our portfolio and talk about more fun projects in the future. So with that, we will stop and take questions. Thank you.
All right. Thanks so much for everyone's great presentation. And then, like I said, if you have any questions, the attendees, please type your questions into the Q&A box, and I will read off them to the panelists. So let me begin with the first one here. So then, I'm wondering, from your talk, how do you define sustainable manufacturing itself, and what are the ORNL, Oak Ridge, and IACMI's primary goals towards achieving that objective?
Oh, yes, thank you. Yes, sustainable manufacturing involves producing products through a process that minimize the negative environmental impact, conserve energy and resources of the process as well as the products. So key aspects, if I wanted to try to explain as best as I can in terms of Oak Ridge National Laboratory site, we developed in our group advanced sustainable materials and products considering their entire life cycle to improve sustainability at every stage. This means that looking at the feedstock, manufacturing, and use time frame of this product. And secondly, in Oak Ridge National Lab, teams are working to enhance the energy efficiency as well as to reduce the carbon footprints towards zero carbon in manufacturing and in building technologies. In manufacturing, there is a user facility, manufacturing demonstration facility. In the building site, there is another user facility in Oak Ridge National Lab located Building Technology Research and Integration Center. And Oak Ridge also work on promote renewable energy integrations into the grid. And also we have a group of scientists and researchers conduct environmental impact research in here. I would also add a group of researchers, scientists, and another user facility is on advanced sustainable transportation technologies. However, when we look at the IACMI goals, IACMI has a slightly different role, and particularly our activities on recycling sustainability. In IACMI, we would like to develop in Composite Institute. We would like to develop materials for mainly automation aerospace. And we look at how we improve the manufacturing process efficiency and reduce the energy intensity. And looking at all these materials, we look at in the production, we try to minimize plant waste and end-of-life use of these products through recycling, reuse, and design. And one big part of the IACMI, I would say, composite workforce development and training in sustainable manufacturing practices. We worked heavily with educating, training the next generation leaders in sustainability within the IACMI.
All right, and then next question is from our attendees Q&A panel. Oh, it was just disappeared. So there was a question about what type of challenges you have encountered when recycling products manufactured from recycled fibers? Uday, can you help addressing that?
Yeah, I'll try. A lot of challenges. Yes, I will definitely weigh in. Yeah, so when you talk about recycled fiber waste streams, a couple of issues always plague the development. One is, of course, the source of the fiber itself. Is it like a fiber that's coming out of the manufacturing waste when it's still in the dry form, like coming out of a edge trim or so? Is it coming out of manufacturing waste from a pre-preg where already resin is on the fiber? Or is it like an end-of-life part where now you're recovering the fiber from that? And a good example, of course, is pyrolyzed carbon fiber, where you start with a, let's say, a decommissioned aircraft door that has to then go through pyrolysis, where the fiber, which is originally continuous woven, has to convert into, or gets converted into discontinuous fiber, because that's the nature of the process. And then in terms of sorting that, in terms of geometry, diameter, uniformity, fiber length, surface issues, like there's a lot of residue on there that needs to be understood. And then being able to cost effectively manufacture that in the secondary processes. So all these, each, what I tried to list or mention quickly, are all individual challenges on their own. And the designer then should be comfortable calling out that material in their designs for lower upper bound properties, because they should be comfortable using that in their designs. So I would say glass cost is a challenge to meet cost effectiveness. Carbon, a lot of the fiber length and uniformity is a challenge. Other fibers are still in the infancy of recycling. But that's in a nutshell. I'm trying to weigh in on that question, Chairman. Yeah.
All right, and then just a note here, I saw a couple of the attendees raise their hands, and if you do have questions, just please type into the Q&A box and I will read them. So another question here is that, again, from Q&A box from attendees here is there any work going on at Oak Ridge National Lab related to separation of fiber and a matrix at a micro scale?
Matt might be a good person to take
I
that.
can, yeah.
Yeah, sure, Dan. Yeah, go ahead.
Yeah, both of us probably just, I will just refer to Matt to answer this question then. Matt, you're muted, I guess.
Yeah, mute.
Right, let's try that. So per my understanding, we do not yet have the capability at the MDF at pilot scale to separate out the fiber and matrix. Of course, we know that there are technologies that can do so that are available at Oak Ridge. You know, solvolysis, for example, is a process through which you can separate out resin and fiber. But at our current capability, that is not yet within the bandwidth. We have a ton of ideas in that space and are really actively looking for collaborators. We know that there is opportunity coming down the pipeline in that space for R&D. However, we do not yet have a scaled capability for doing that.
All right, thank you. Another question is from the webinar chart. Maybe Sona, you can help with that. And what challenges do small and mid-sized business experience in general in joining the band, and what are their technical and business process challenges?
So was that for me?
Yeah, I guess so, because I guess this we're talking about if a small or mid-sized business want to work with ACMI or Oak Ridge, and what type of challenges they typically encounter from both technical perspective as well as business perspective.
Sure, thank you. Thank you for the question. So I will try my best to address it. In terms of challenges that can come forth, we are a user facility and we try to enable industry to move forward and progress, but we are dictated by Department of Energy related paperwork, and it takes time. If you're trying to come in and work on a project in a few weeks, that is not how quickly we are able to work through. That's more on the programmatic side, right? On the technical side, why would we want to pick and work with universities? We work with over 50 universities in more than 200 industry partners. So what makes someone unique enough to stand up and say, yes, we should work on them? Anything related to manufacturing process, if you're enabling that, if you're enabling material development, if you're enabling a software that would assist in both either on the material side or also on the manufacturing side, and this is bringing in advanced technology to the US, or you're working in something on the side that will enable more domestic work coming into the US. These are all areas that we are always trying to make sure that we are keeping in mind. So we select our industry partners along with that, based on that. There's also the objectives and goals that have been put forth from the Department of Energy, from the manufacturing demonstration facility, and we want to make sure that we're working on those areas. So a couple of good examples would be what Halil just mentioned on the bio-based material side, what Matt mentioned on the composite side. There's traditional from the SAMPI community. You work with long continuous fibers, you're working with woven materials, and majority of them are thermosets. Can thermosets be recycled, or does it only have to be thermoplastics? And then how long can those thermoplastics be recycled? From the bio-based material side, is it only going into land? Is it biodegradable, or can you recycle bio-based materials? Those are all things that we are working with. And taking a bio-based material or a recycled material and putting it into a manufacturing process, like Kate and Dr. Vedya mentioned, these are systems that are built, and we have more knowledge of virgin material going into that. But working with recycled material and changing those process parameters to make sure when we start scaling up, we're hitting those at the right times and the right volumes and making it cost effective. Those are all areas that we are always looking for, and those would be good ways to go through. If you're not falling in those categories, there are some wiggle room in just trying to understand, what is your technology, what's your idea, and what is it enabling? Are you going very narrow to one industry type, or are you able to take this research and learning to apply it to multiple markets? Those will be things that we would look for. Sometimes if we're not able to hit that, then that would be a challenge to work with that industry partner.
So Sana, to add to your great discussion, so to the colleagues' question on the challenges for small companies to work with IACMI, for example, or other. So honestly, there is no specific challenges as such. It's really more of the exchange of information of what the interest avenue is, what the technology that you're looking to pursue. Are there assets and skills within the institute to help you kind of engage and provide the support? In terms of the project creation mechanism and execution, it's pretty well set now with so many years. Even a single person company, a very small company of 5 to 8 people, or a medium size. So the projects would be agnostic to the size of the company. It's more of the technical idea, and does that move the needle forward? I would say that that's really where the metrics are looked at.
All right, cool. And then next question from Q&A and box, and this might be a little bit specific. So what textile products can be produced at your lab that are comparable, commonly known as the textile preforms or for composites, such as woven fabric and things like this?
I'm sorry, Gwen, can you, are they asking about
I guess,
creating woven?
Yeah, I guess this person was asking like a little bit specific of what type of textile products can be produced that are comparable with conventional counterparts as the textile preforms.
Okay.
I think the mats, I think Kate also touched that, but wovens and CF's mats as well.
Yeah.
Let somebody else take it, then I'll wait. Okay.
Kate, do you want to take that?
Sure. So I would say that some types of products that we've been making, so we do a lot of non-woven fiber based composites, and we've been making various compression molded products of those, both through like more of a conventional means, but we also have an induction molding tool that we can use to do very high temperatures very quickly. So think like wheel wells, more simple geometries is what we have the ability to do in-house, because we're very focused on demonstration. So we don't necessarily have specific part tools. We have more general purpose molds for those types of things.
All right.
If we add that one is new pilot scale facilities to make a yarn, to make a different type of mat from a short fibers is within our capability as well. Maybe you can allude a little bit more, Professor Vaidya, on this area.
No, it's a great question. Actually, it's a little open-ended question. That's why I'm kind of being skirting around. But when you ask about comparable materials, you should kind of look at which box you're talking about, discontinuous or continuous, because the property bounds are very different there. But like Soidan and Kate said, we do have almost a very broad range of tooling to de-risk the application development. So if a material supplier wanted to see how their material works in a tool, in a continuous fabric, comparing to, say, a discontinuous deep draw part, we can provide a lot of that information through the collaboration, which then would help the collaborator or the company to take it to the finish line much more quickly than spend a lot of time upfront in researching on their own end. But in terms of recycled fibers, except solvolysis, most of the continuous fiber gets reduced to discontinuous. So you have to find ways to maximize properties from discontinuous by way of alignment, fiber length, entanglement. Those technologies are something that are already going on in the background. But then using that in creating the product is something that will be very specific to the product. We can't provide like a one size fits all solution. So.
All right. The next one here is about a question regarding, can the circular economy approach be applied to materials other than composites, such as pure metals or their alloys? And is there any active industrial collaboration in this area with Oak Ridge National Lab right now? Something just beyond composite, I guess.
Soidan would be a good.
Yes. I will actually say that metals and are probably the most recyclable materials at this point compared to polymers and composites, and absolutely circular economy apply to anything we use in our daily life. And we particularly focused on how we do recycle the polymers, composite fibers, and so on, since metal is a more mature industry at this point.
Cool. And the next one.
And also Dr. Corey runs some polymer composite projects. Maybe he can actually add some on the metal side.
Yeah, so that capability kind of goes beyond the expertise of the specific scientists on this call today, but there are 6,000 of us that work at Oak Ridge. And so one good example of this, we have a project with the Wind Office right now in collaboration with the National Renewable Energy Lab, as well as Sandia National Lab, where we're looking at the recyclability of all of the materials in the end-of-life supply chain for wind turbines. So, of course, I'm more of an expert on the wind turbine blades, which contain a majority of composite material. However, the towers, the generators, the magnets, all the other materials in there are also being explored. And so there is a ton of recent development in that. I'm more than happy to share with anybody on the call the upcoming reports coming out of that team. But there's a lot of interest across the lab, just outside of this specific knowledge base.
All right. Yeah, so next.
Professor Quinn, I see another question actually in this chat. Maybe either we missed that one or we may have two two chat is coming from our side as well as. Would you mind if I read this question?
The one in the webinar chart?
The chat that I see right now
Yeah, of
about
course, feel free to do so.
Yeah, question is about, do you have the capabilities for applying chemistry and sizing on woven or non-woven beyond the ability to apply it to tows? Specific interest in applying it to the bio-based format. That was another question I think we missed there. Yes, I asked the question. I can answer the question, but probably Kate or Halil, would you like to add on this question?
I can quickly add, I think it's very similar to the previous question about how to process, but I think right now in smaller scale, we are working on deep coding type of approaches for, these are like, again, most of the time like discontinuous fibers, but also combining it with other processes like wet laid or other processes in which fibers are, when they're converting to mat format, the sizing can also be done in situ. So this kind of approaches will definitely help. And it is, the perspective comes from both recycled fiber and then the natural fiber side, because they're both in the same form. They're in like a bulk form. They're not organized or bulky form. So processing them, feeding them, those kind of issues. But one approach is combining this kind of processes, as well as second approach is, again, even the bio-based materials can also be spun or like yarn, be woven into yarn so that they can continue to convert into continuous fibers, which can then be processed with other continuous fiber processing equipment.
Yeah, and also Halil, that's a great feed, right? So I do want to mention to the group, or because of interest, we have just added a very state-of-the-art sizing line from Michelman. Thanks to Michelman, they have actually enabled this line, consigned it at our facilities at IACMI, UT, and Oak Ridge. This is a 70 feet long line, completely modular, which can really enable a huge range of chemistries and ideas. So if somebody is looking at woven, discontinuous, there is actually a very unique way of evaluating that on a pre-commercial scale. And I think there was an article put out about a month ago, and if anybody particularly is interested, we'd be happy to share more on that.
All right, I will add my last 2 cents here, the last 2 cents in this topic. So as my colleague said, working with discontinuous fibers, which often recycled fibers as well as natural fibers are, we worry a lot about the interfacial chemistry, since that will play a big role or a significant role in the composite properties. So they talked about some of the sizing techniques. We're also doing some spray-based methods, but those are being developed currently, so I can't say too much. We do both commercial sizing agent application as well as developing our own chemistries that are specific to the composite system to address specific challenges. So I'll give you an example. For instance, in natural fibers, we look at chemistries to reduce water uptake, for instance, or to improve thermal stability.
All right. So next question is about thermoplastic composites, I guess. So the question is about, have you ever worked on recycling thermoplastic with fiberglass or carbon fibers? And do you think it is feasible to recover the full fiber without cutting from thermoplastics by melting the thermoplastic away or even reusing the thermoplastic resin again?
Matt, do you want to take that?
Sure. I apologize, everybody. I've been taking questions in the Q&A as best I can. I'm normally quite vocal, but there's a lot of great questions, and I'm hoping to see if I can answer as many of them as I can in the chat. So yes, we have been doing a lot of work. Let me just pull up the question to make sure that I answer it correctly. So we do a lot of work in recycling of thermoplastics with fiberglass and carbon fiber. So we one of the things that we have found is that, so, when we were shredding stuff at the small scale, we were seeing significant impacts on fiber length, on, reground granulate from thermoplastic composites. But when we scaled that up to larger scale systems like our 4,000 pound per hour throughput shredder system, we saw really no significant impact on the fiber length associated with the size reduction pathway. However, we did see that fiber was falling out. We were losing fiber content. So we lost fiber, but we didn't lose fiber length on average. When we recycled those materials, we actually do see we did not see a significant reduction in the mechanical properties of the recycled materials from that process. Most of our fiber length reduction that we're seeing is coming actually from the compounding process, at least with our line. When we do the recycling at scale, at like manufacturing scale, pilot scale, that's what we see. So it is potentially feasible to look at recovering the fiber at full length without cutting it, basically just melting out the plastic as you indicated. I would be curious to see what recycling technologies are capable of doing that at scale right now. But what we have found is actually that when we grind up the plastic, we do not see a significant reduction in the fiber length of the reground plastic. It's really coming from the compounding process. And so if you take those fibers and you put them back into the compounding line, it is likely they will still break anyway. So that's one of my thoughts on that question. It's a great question.
All right. So the next one is from a question actually is from Europe, because this person was asking, in Europe, key accounts are increasingly demanding a minimum percentage of recycled materials in the manufacturing of composite parts and looking at the LCA of the composite products. Is this trend same in the USA as well?
I can take the first part and then see if anyone else wants to address it. So thank you for the question. What we are seeing in today's market, especially in the US, is we don't have a policy or a requirement, but from different markets and industry OEMs, original equipment manufacturers, we are seeing an uptake of being more conscious because the consumer is asking for it. And related to that, there are certain OEMs who will not touch any new vendor, or even in their existing vendors, they've given very clear requirements that you need to provide a full picture of where your material is coming from. If you can give us the LCA of that, and also do a techno-economic analysis so we understand the feasibility of it and where will that material at the end of life be reused into. So these are requirements that only a handful of markets are now asking for, but we definitely expect that to grow quite a bit. And with all the new funding opportunity announcements that are coming out from the Department of Energy, be it the Advanced Materials Manufacturing and Technology Office or the Building Technology Office, we are seeing quite an increase of every single proposal requires us to conduct a life cycle analysis. So we are able to show the feasibility of this and what would it look throughout the supply chain. So that would be my response and open it up to other panelists.
All right, if not, I'm going to keep moving forward. The next question is, what tools do you have to evaluating the sustainability of bio-based feedstock for composite materials?
Is this the question is what type of tool to evaluate the bio-based composite feedstock?
What type of tools do you have to evaluate the sustainability? I guess they talk a little bit on LCA tools, things like this, or?
Yes, I would say directly the first thing that we would like to see is the LCA, a life cycle analysis. And we do have a life cycle analysis person in our group, as well as there's a team just focused on life cycle analysis in Oak Ridge Nation Lab. We work them very closely. First thing is looking at the life cycle analysis to understand where it stands in terms of sustainability.
And just quickly add on that, as I explained in the previous project, that we are actually doing a lot of like case projects where we're looking into how the material properties are changing, the fiber material properties, polymer properties, even the biopolymers. And we're investigating all the changes upon multiple cycles. So actually LCA and TA tools are great to give you initial idea, but you have to still see that, because depending on how many times you can recycle and you preserve your properties, then every cycle your actually LCA calculations changes. So we are looking into that. If once you start to go third, fourth, fifth cycle, then your impact really goes down at the end, especially if you do not have to repelletize your material into specific pellet shapes.
All right. Next question here is there any particular interest or efforts in incorporating sustainable manufacturing approaches to desert regions? For example, is there any specific desert-based natural materials of your interest that could be applicable to your R&D approach?
It's an interesting question. Our R&D approach, of course, when we look at the sustainable manufacturing perspective in general, it is probably applicable to desert area as well. However, have we done specific study? What are the resources? How we apply? From my side, I would say I haven't done, or we haven't done, but applicable to, of course, the desert area, like any circular economy, any sustainable practices.
I may jump in here super briefly.
Yes.
John, I just wanted to let you know that question was asked by Dr. Sunjin Kim from the University of New Mexico.
Oh, okay. I got it then. Please, you go ahead and answer that.
I just wanted to highlight that Dr. Kim was a former member of this team. I wanted to say, when we think about desert resources, this is a really interesting question. So I'm just kind of parsing through this as it's asked. When we think about resources that may be available in the desert, especially in the U.S., we would tend to see perhaps, at least in the Southwest, maybe some really good solar resource from when it comes to sustainable energy, as well as potentially, if we look to like Eastern Colorado, I'm not sure if we would consider that desert region. But if we think about that portion of the country, I think there's a lot of resource available potentially in end-of-life sustainable energy generation technologies. I know there's a lot of R&D going on for solar resource. I certainly can't speak to what resources may be available like underground in terms of mining, but in terms of end-of-life material, I certainly think we could think about some of those sustainable energy application material systems and seeing if we could drive value from those.
I'll add on here. I think sisal fiber is really interesting. I also think agave plant waste for the creation of, like, say, cellulose nanofibers would be interesting. Anything that's cellulose based that might be a good source of cellulose from the South, I think would be a candidate, but I haven't looked too much into it thoroughly.
Yeah, I wanted to ask, I think Soydan initially, when we started, had mentioned, the three pillars: industry, government, academia, and how associations like SAMPI can contribute. Do you think SAMPI, from an educational standpoint, could help more on this? As Caitlin just mentioned on the, cellulose materials, do you think there's an opportunity for us to further educate our community on these I'm not sure if all our small mediums know what's available out there.
Well, that's a great question. I think education is part of any of us. We can contribute to education, and SAMPI could play a great role as they've been leading all these activities for us for year and their service. And SAMPI is I'm sure there are education programs, but SAMPI could be in sustainability. It could be a platform that the people get together and discussions and meet the students with the industry as well as scientists and researchers. Could be a platform. And I would say SAMPI is the place that engage the opportunities with students as well as the industry. And further develop some other short courses, micro credentials, even maybe all the way goes to curricula, working with academia as well. And these are activities thought through. There are a couple of them that came to my mind and we mentioned. And for the education system within IACMI, as I said, we have trained many students. They've been in SAMPI conferences, they've been in SAMPI chapters, and they've been actually part of it already. Another example that research experience for undergraduate program within our core research, Dr. Kate Clarkson is running this program, and there is a lot of learning experiences actually we can also transfer to SAMPI from that program, I'm sure.
Excellent. I think, I think the technical committee that you head up, I mean, this is an ideal platform that we have to get very much closely to all the great work of IACMI, you know, the Oak Ridge and everyone else. So, I know you've invited speakers many times on the topics.
Yeah. I think that's I agree. I think SAMPI can definitely play a very important role, and then our tech committee on sustainability will definitely look forward to collaborating with all people from different sectors in the ecosystem to work together moving forward. So really appreciate this opportunity. All right, is there any other questions here? As far as I'm aware, we sort of finished all the questions here, and then we only have 2 minutes to 1 p.m. So perfect time as well. All right, so if there is no more questions, I would like to thank all the speakers again. Thanks for great presentations. Thanks SAMPI for organizing this great event, as well as looking forward to keep discussing this topic. Like I said, we will have our slide and then video available to the attendees in about a week. So look out for a potential email from us too. So, all right. Thanks everyone. Appreciate all your time and interest.
Thank you. Thank you for the opportunity. Bye.
Thank you for the opportunity. Thank you for joining. Bye.